Righty. Okay. All right. So far, to recap, the X-rays, we're talking about the PSP plate. When the X-rays come into the PSP plate, what is it that they are interacting with?
Electrons.
The X-rays, when they come into the plate, are interacting with
The crystals.
And what acting with what? I couldn't quite hear. They're interacting with the phosphor crystals, and they're made of what?
Barium fluorohalide with a dope of europe.
With europium, right. So the barium fluorohalide, those phosphor crystals are ionized, which means they release the electrons. And then those electrons, they're in an excited state. We don't want them to recombine back with the barium fluorohalide. So the europium is there to serve as a trap. So it will trap those electrons. That's our image data. So now we need to get that image data extracted in order to have it come up on the workstation. So the cassette is placed in the reader device, and that plate will come out, and it will be sent to something that's referred to as a scanning assembly. So the plate will actually go through this scanning assembly here. So what happens is the plate will travel down this direction. It'll go into this scanning mechanism, and there is a laser in there. And the laser is going to scan the plate. It scans the plate like top to bottom, left to right. So it scans it top to bottom, left to right. So every segment of that plate is scanned. You may hear, any of your book uses this terminology. They refer to it as a point scan, So it's scanned top to bottom, left to right. And to kind of give you an idea as to what this looks like. And your book has fairly decent images as well, but I like this one just a little bit better. In the scanning assembly, the plate is scanned. I told you referred to as a point scan. Your book uses that terminology too. But some of the terminology that you need to know is slow scan versus fast scan. Slow scan refers to the direction that the plate is traveling. Okay, direction that the plate is traveling into that scanning mechanism. And it's referred to as slow because the plate does move slowly. Fast scan refers to the direction that the laser is scanning the plate. The laser scans the plate in a perpendicular fashion. That's over here. What is it? It's showing you there's a laser off to the side. I told you that there's a mirror type of device in here. So here's one of the mirrors. So a laser beam will bounce off this rotating mirror. It shoots the laser beam over here, and it reflects it down. And basically, this is what it looks like. The laser ends up scanning. So the laser, it reflects down, and it's scanning perpendicular to the plate. What you do need to know is that slow scan is the direction the plate is moving. Fast scan is the direction that the laser is moving across the plate. And so the laser always moves, as this plate moves through, the top of the plate gets scanned, and it gets scanned all the way to the bottom of that plate. Okay. So that's what's happening in this scanning assembly. Okay. So laser scans the plate. Like I said, I told you, there are mirrors in here to reflect the laser. That's not something I get hung up on, but it is important to know that it is a laser that is scanning the plate. Okay. But there just has to be some way to direct that light to the imaging plate, and that's why you have mirrors in here. But it's a laser that scans that plate. And in actuality, that laser is a red helium laser. It emits red light. It's a helium laser. So here's a here's a bird's eye view of the laser scanning the plate. So this is the direction that the plate will be traveling. So that's what's referred to as the slow scan. So this is like a bird's eye view. You know, if we were on top looking down at the imaging plate. So this is kind of what it looked like. So there's the plate moving through, and there's the laser. And the laser scans faster than the plate moves. So the laser, it's referred to as a fast scan. The direction the plate moves is referred to as a slow scan. But it's scanned from top to bottom, left to right. Every segment of that plate is scanned by the laser. So what happens is when that red helium laser scans the plate, it excites these electrons that are trapped in the europium. So it gets them excited. So it raises those electrons up out of that energy trap, because energy is imparted to those electrons by that helium laser. So the electrons get excited, they come up out of the trap. Well, the thing is that electrons, you know, they're in an excited state, but they will end up losing energy. And when they lose energy, then they end up going back and recombining with the barium fluorohalide. Okay, and that's okay at this point. Now, we didn't want these electrons to recombine with the barium fluorohalide when we had just taken our image, had made our exposure, because we would have lost our image data. But now that the plate is in the reader, it's okay for these electrons to get excited and for them to drop back down and recombine with the barium fluorohalide. Because what happens is, you know, the whole thing with conservation of energy, these electrons, they have energy. And when they get excited and rise up out of here, as they start to fall back down to recombine with the barium fluorohalide, they lose energy. It's the conservation of energy. So those electrons give up energy in the form of light. So see, we would not want this to happen before we get the plate in the reader. So that's why there's europium there, because when those X-rays come in and interact with the barium fluorohalide and releases those electrons, we need for the electrons to be trapped, because otherwise we would lose our image data. What would happen is those electrons, if we didn't have europium there, the X-rays would cause ionizations with the barium fluorohalide. So those electrons, they would fly out of their shells, but then they would immediately come back down and recombine with the barium fluorohalide, or even go into other atoms and fill voids there, and we would lose our image data. And yeah, they would give up light, but we don't want the light to be given up before we can end up getting our receptor over to the processor, because now this light is our image data. So our image data, started out as X-rays, got converted into electrons. Now when that laser scans these electrons, they come up out of their trap, and as they lose energy, they give up light. So now our image data is in the form of a light photon. So you with me so far with those steps? So X-rays go to electrons, electrons get trapped, the laser scans it, those electrons jump up out of those traps, and as they start to fall back down to what we call ground state or recombine with their barium fluorohalide, they release light. That is our image data. Okay, so light gets released from the PSP plate when the laser scans it. Now, that light is our image. We don't want to lose that light. So there's a device here that is referred to as a light guide. There are fiber optics in here. That's why it has this kind of swirly pattern to it. So the light will be taken up by the fiber optics and then transferred to a photomultiplier tube. Okay? So the light guide will pick up the light, because that's our image, and it will send it to a photomultiplier tube here. That photomultiplier tube, what it does is it takes the light and it converts it back into electrons or an electrical signal. Okay? It's an electrical signal. It converts it back into electrons. That's our image data. You may also hear it referred to as an analog signal. Okay, we'll be talking a little bit more about that. So that's what happens. So we do start out with X-rays, and ultimately, in the end, we end up with electrons. The photomultiplier tube converts light into electrons. And we won't go into detail about what the photomultiplier tube is made of and the materials that it consists of, but it is a solid state type of material, type of conductor. Okay. All you need to know is that we end up with electrons. Okay. So you okay at that point? That whole process there? Okay, because you may have to list out those steps, all right? So then what happens after that plate is scanned? What happens to it? Well, that laser doesn't release all of the image data. Believe it or not, there's still some residual electrons that are trapped in those energy traps, in that europium. And we have to completely get rid of that remaining energy. So the plate goes through something that is referred to as plate erasure. There are fluorescent lights in the reader. So these are the fluorescent lights that are in our reader. So this was taken out of our unit. And these fluorescent lights will release the remaining trapped electrons. Because if we don't, then what happens is, if we make another exposure, we could end up with a low contrast image because of that remaining data, or we could even end up with ghost images. So you might take a hand x-ray, and if all that data is not erased, and now the next image that you're going to take is a skull, you could end up with a skull image that also has a hand on it. So this mechanism will erase those images.
Is there a higher chance that there will be, energy still remaining based on how much exposure it receives? Like when you talked about some of the plates needing like time to, or do you have to run it through more than one time ever? Like when you're just demonstrating like overexposure?
You use, the normal typical exposure, you're like within your exposure indicator range, or even if you're a little, higher than the exposure indicator range, a little too much exposure, the erasure lamps can erase it. Okay, so when that plate comes back up through here, these lights turn on and it can erase that data. Okay, so I'll come back to that question in a second, Casey. I'm kind of getting there. But does it make sense why when you first put it in, these lights don't turn on? We don't want these lights turning on as soon as we put that plate in the reader, because then what happens?
It'll erase it before you have a chance to.
Yeah, it erases the plate. Okay, so it goes down here, the data gets scanned off the plate, and then when it comes back up, those lights turn on and it removes the rest of the data. So when you do a typical exposure or you're slightly overexposed, these lights can get rid of that extra information. If you are too overexposed, more like towards the end, side of being grossly overexposed, then you may very well get a message on the reader device that tells you to run it through another erasure cycle. You can do just an erasure cycle without running the plate through the processing mode. And I'll show this to you one day when we come back and we're down in the lab, how you can just simply, there's a button you can push and it will take the plate out, and it'll only run the plate down to here, turn the lights on, and then put it back in the cassette. So if you're maybe more towards grossly overexposed, the unit will tell you, hey, I couldn't erase all the data. You need to do another erasure cycle. If you're up along the lines of detector saturation, you'll get a message that will say, basically, I can't handle all this data. You need to take this plate, this cassette, and you need to set it aside for 8 hours and let the energy just dissipate on its own. Do not use this plate because you will end up with low contrast images. You'll end up with ghost images. There's too much remaining image data on this device. So yes, it is possible to have too much information left because the exposure was so high. So that answer your question? Yeah. Yes, that can happen, and that's unfortunate when that happens. Okay. Now, the thing about these erasure lights is that you do need to replace the bulbs when they're burned out. So I'm dreading the day when that happens and having to do that because that's a production, to replace those. And you can usually tell when the bulbs have burned out because it's not erasing correctly. We end up with low contrast images and ghost images. And it's because the bulbs are burned out. So if the bulbs are burned out, there's nothing there to erase the image data. Something else that you need to know about these, even though I realize, in clinic, you all are not using these on a regular basis. Very few sites have these anymore, but you never know. You need to erase the plates if they have not been used in at least 48 hours, as well as if the plate is grossly overexposed. I told you I'll show you how to erase the plates without putting them through the whole scanning mode because they don't need to go down to be scanned by a laser. We're not interested in extracting that data for an image. We just simply want to get rid of the extra remaining data because we don't need it. We've already got our image. So if plates are grossly overexposed, you need to erase the plate. And if you haven't used it within 48 hours, because otherwise you end up with low contrast images or ghost images. So when we have lab on a Tuesday, those plates, they've been sitting since Thursday because we only have lab on Tuesdays and Thursdays. So when we have lab on Tuesday morning, I go in and I erase the plates that I know we're going to use because they have sat for more than 48 hours. Remember, digital detectors are remember that wide dynamic range, they're extremely sensitive to background radiation. So just sitting for over 48 hours, they accumulate background radiation. And I don't want that on my image because that'll give me a low contrast image. So this is an example of imaging plate that it sat for 72 hours. So let this plate sit for 72 hours. And what I did was processed it. I processed it, and you see how it accumulated background radiation. Because if I didn't make an exposure to it, that plate should pop up. It should appear white on the workstation. But it appeared like that. And that's just from background radiation. That was after 72 hours. It will look very similar to that even after 48 hours. Okay, so that's the rule of thumb. You have to erase it after 48 hours. Here's an image on what we call a fresh plate, a plate that had been erased. Here's an image on a plate that was not erased after a 4-day weekend. So that plate sat for 4 days. See how low contrast that is? It's a terrible image. Terrible image. Not good contrast to noise ratio, is it? So it could be hard to distinguish low contrast structures. If there were any, soft tissue abnormalities in there, it'd be very hard to pick that out because that contrast is terrible. So that's what happens. That's what it could end up looking like. Okay. Oh, let's see, flat panel detector. Let me see. Flat panel. Indirect. I'll tell you what. Are your brains full?
Mm-hmm.
A little bit. Okay. How about we go ahead and we'll stop here?
Thank you, Jesus.
Is that okay?
Mm-hmm.